Good morning. I am going to offer you this course on principles of physical metallurgy. This obviously the first question that comes is what is physical metallurgy? It deals with evolution of structures in solid as it forms from liquid, then effect of alloy elements and impurities on the transformation process, and effect of processing techniques on evolution of structures and structure property correlation. And main focus although will be on metals and alloys, but people in other related discipline will also find this course useful. For example, whether it is ceramic, polymer or other fields of materials. Metals and alloys have been in use since ages. In fact, several periods of human civilization have been named after metals and alloys. For example, Bronze Age or Metal Age, but in true sense, the way we know metal today in bulk, this science and technology is not that old. It is only since 18th and mid 19th century metals and alloys were available in bulk. In fact, first time with the introduction of Bessemer process and around mid 19th century, it was possible to produce steel in bulk quantity, which is one of the main material of construction today. Now, objective of this course is to provide a basic understanding of the underlying principles that determine evolution of structures in metals and alloys during their processing and its relation with their properties and performance in service. And metals that we use, they are produced by selected processing techniques, and its properties are controlled by the structure and composition, and the performance of this material are in turn controlled by properties. It may be a good idea to have some knowledge about annual production figure and some of the properties of few common metals and alloys, which is listed here. So, steel is possibly the most widely used material of construction. See, 1.3 billion metric ton of steel is used in a year is produced, and India stands 5th in the world in terms of production figure, and current production figure is around 55 million ton. And this figure gives you how we can alter the properties of steel. It has a minimum some strength of from 240 MPa. By controlling processing and techniques and heat treatments and others, you can reach a strength level several times higher than this, around 10 times or so. Same is aluminum. In fact, aluminum also became available in bulk in the beginning of 20th century, and this also gives the figure of copper, another common metal, and zinc. And metals are very popular material of construction because of its unique properties, the strength, formability, toughness, and electrical and some cases magnetic properties. And in this course, we will it is necessary to have some basic idea on the atomic bonding and crystal structure. So, we will start this course with some preliminary concepts of atomic bonding, crystal structure, because in the later to understand many of the processing techniques, it will be necessary to have an idea of atomic bonding and crystal structure and the way the crystal structures are represented and what we know about crystal orientations and how these are represented graphically in stereographic projection. And in order to know about metals, we often use number of experimental tools and techniques. We will be talking about microstructures, and to look at the microstructure, we use different types of microscope. It ranges from optical to scanning electron microscope or transmission electron microscope. The underlying arrangement of atoms are actually have been studied using X-ray diffraction techniques. We will also be talking about number of mechanical properties, and so it will be a good idea to have how are these properties measured and how do we look at the transformation processes where thermal analysis is quite important. So, it is true a detailed course on this certainly cannot be covered within this intended 2 hours, but I will try to give some basic understanding which will help you to understand subsequent lectures. Then we will start with the solidification of pure metal. The metals that we use are all they are solid, how it is produced. So, we will start with the transformation processes that goes on during solidification of pure metal, the basic concepts and basic principles of thermodynamics, which will thermodynamics as well as kinetic, which will help us understand development of structures in pure metal. Metals have an attractive property that it can be shaped by mechanical processing, which is known as plastic deformation. And we will start with the process plastic deformation of pure metals, the look at the mechanisms by which deformation takes place, not only in a single crystal, then in a polycrystalline material. We will have some idea about the theoretical strength of ideal crystal. Next, we will know about some of the crystal defects in metals, the properties of metals determined by the defects that are present, and we will know about the type of defects and how these defects affect different properties. Of all properties, it is the mechanical properties which can be changed by several or by possibly an order of magnitudes. Not only mechanical properties, other physical properties are also affected by this vacancy, and we will try to give you some idea of that. Now, metals alloy that we use, they are made up of more than one element or more than one metal. So, here one important criteria, one important mechanism is how do these atoms of different elements, how are they distributed, what are the factors that controls the movement of these atoms and the lattice, and this process is diffusion. We will have an idea, preliminary elementary idea about the phenomenological process of diffusion, and we will also look at the atomistic approaches. With this basic background, we will start with solidification of binary alloys. Binary alloys are classified in different groups. We will look at how the structure develops in these binary alloys. We will look at some of the 3-phase equilibrium like eutectic, peritectic, some solid state transformations. We will know about the origin of structures in cast metals. We will try to explain what is segregation, porosity, and then we will look at one important phase diagram, iron carbon diagram, which explains or which explains why the properties of iron carbon alloy, why does it change that, and what type of processing it can be subjected to. We will get some idea about few common binary alloy diagrams and their characteristics, and how to interpret the evolution of microstructure from and their relationship with properties. Now, metals can be subjected to cold working, and what is actually cold working, what are the properties that change with cold working, and how can you restore the properties and control the subsequent processes like and it will be primarily a phenomenological and mechanistic approach. We will also know about the process of precipitation hardening, what happens when a supersaturated solution is given some thermal treatment. We will know about the thermodynamics and kinetics of precipitation. Now, we will look at the heat treatment of steel in detail, the kinetics of the transformation, time temperature transformation diagram, some of the terminologies like parletic, martensitic, benetic transformation, effect of alloying elements on phase diagram, TTT diagram, continuous cooling diagram, and some of the common heat treatments. And the end, I will give you some idea about applications of physical metallurgy. That means how the strength can be of a material or metal and alloy can be increased without sacrificing ductility or roughness. We will look at thermomechanical processings, microalloyed steel, the scope of producing very high strength steel, look at the evolution of superalloy, how that has developed, and control of textures and materials. So, in total, in this class, if you add up the number of hours, it may come to around 44, but I hope I will be able to finish within these, and as the course progresses, we will see exactly how many lectures it will take, but certainly it will not be more than around 48 hours. Some of the common textbooks, good textbooks which are listed here, you can refer to these. Many of these try to give you a quantitative descriptions on structure property correlation. You will also need to refer to some of the handbooks where the material property data are listed, and some of the problems or exercise that I give, these reference book will be helpful in getting you the data that you need to solve the problems. With this basic understanding, I will now begin with the first lecture, and in this I will give you some idea in brief about atomic bonding and crystal structure, and but with a primary focus on metallic bond, the crystal structures, the system that we use to represent crystal planes and directions, and how the crystals, they are solids, how different directions and planes and directions of a crystals are represented in a projection called stereographic projection. Now, this slide gives you influence of atomic arrangement and microstructure on properties. So, typical properties which are listed like mechanical, electrical, thermal, magnetic and chemical. Out of these, it is the mechanical properties which has a strong dependence on crystal structure and crystal defects. It is not that the others are not dependent. Here also crystal and crystal structure does affect the properties, but it is not to that extent it affects mechanical properties, and as we go along we will see why. Similarly, a level higher than that is a microstructure. At a microstructure level, when we say microstructure, it is a structure that we can see under an optical microscope and or electron microscope. I mean, we are talking about a structure which is beyond the crystal structure, larger than the crystal structure. And here also the mechanical properties strongly depends on microstructure, and this is also, this dependence is much higher than in other cases. And just to recapitulate things, this we know already, that atoms are made up of subatomic particles. You have a nucleus where you have the total mass which is concentrated. It consists of proton and neutron. The proton is positively charged and number of proton is equal to its atomic number, and A is the atomic mass number, A minus Z is the number of neutron. So, this is the nucleus where you have the entire mass, and then electrons keep moving in different orbits, and the state of energy in these orbits is described by a set of quantum numbers which are listed here: principal quantum number, azimuthal quantum number, magnetic quantum number. And principal quantum number describes this main orbit K, L, M, N. These are represented by integers 1, 2, 3, 4. And azimuthal quantum number, this is 1 less than the principal quantum number. For K, you have 1 orbit, this number is 0. Magnetic quantum number, this is also 0. Same as you go up, the number of cells go on increasing. Say here you have S cell, then you have a P subcell, and in P you have 3 magnetic quantum number, and each of these orbits, they can occupy 2 electrons and each having opposite spin. That electron, it can move either clockwise or anti-clockwise. Depending on that, this cell will have a capacity 2. Here you have 3 subcell. So, this P cell we will have a capacity of 6. Same way you can look at the subcell D. Here this has 1, 2, 3, 4, 5 magnetic quantum number. So, here this will have a capacity of 10. I will leave this as an exercise for you. Please try to fill this up. And the way these cells get filled up are given in this diagram, which is known as Madelung rule. This gives the sequence in which orbits are occupied by electron in an atom. So, first we will draw a line here. This first is S cell, that is 1 S K. Next it starts this, and then it goes here this, and this arrow gives the way these cells get filled up. And this slide gives some example of how these cells are filled up. I have taken cases of inert gases. Say here you have closed outer cell. If you go back to the previous, try to recollect that one S cell has a capacity 2. If this is full, this is the case in helium. Next is neon. Here the last cell, it has this orbit with a quantum number 2 has 8 number of electrons, and this 8 electron in the outer surface means this outer cell is closed. In this case, whenever the outer cell is closed, it has a stable atomic structure. It will find it extremely difficult to form atomic bond. And these are characterized by the fact that they have low melting point, low boiling point also. And some of these which are listed here, helium melting point is 1 degree Kelvin, but as you go up, helium, neon is a down this group in periodic table, neon is a 24 K, argon 84 K, and down below radon it is 211. We will see later why, as you go down the group, why this melting point goes up. So, the most important criteria of the stability of atomic structure is closed outer cell, and which you get in inert gases, and these are the elements where the bond is weakest. Next stage is half filled outer cell. So, most of the cases you have that outer cell has a capacity of 8 electrons. Now, in certain cases, say like carbon, if you look at the structure of carbon, its atomic number is 6, and this is, if you follow that rule which I just talked about, this should be the structure 1 S2, 2 S2, 2 P2. But in this case, there is a tendency that in one of this electron goes over to P, and all of them they have parallel spin. So, something this is represented by the negative spin minus Px, Py, Pz. So, in this case, this orbit they become hybridized, we call it sp3, and each of these they have same energy level. In fact, this is the type of bonding that forms in diamond, and in fact, in case of a diamond, say since you have 4 identical bond forming. So, what you have a carbon atom, you have 4 bonds, and they are all at same angles. And how is this possible? And this angle is in 3D. The way this can happen is, imagine that you have a cube, and this carbon atom is located at the center of the cube. You join this, each of these corners. these corners which I have drawn by the form line. So, take this. So, here look at this, is one carbon atom and at the center which is connected here. It actually forms what I mean separately as a tetrahedron structure. With the carbon here, and so it has 1, 2, 3, 4 points, and this carbon is located here, and so you join these points. So, you have 4 bonds and try to find out what should be the angle between these 4 bonds which are equal, presented at equal angle, but in a 3 dimension, and you will find out this angle comes to around 109 degree. Once we go through this crystallography, you will get an idea why this happens. Another important point which comes up when this atomic bonding takes place is the Pauli's exclusion principle, that no 2 electron can have the same quantum state. Now, with this background, let us look at how the metallic bond forms. When the atoms are isolated, they are far apart. In that case, this is the atomic structure, some of the cases we see, and the outer shell in metal usually have less number of electrons. They are far from being closed. So, many of the good conductors are monovalent, they have 1 electron at the outer shell. When they are far apart, something you can say, we assume that is the ground level, the energy is 0. As you bring these atoms closer, what happens? 2 kind of forces they interact. One is the attractive force, and this goes like this. Another is when you try to put these two to press together further, there is a repulsive force also. And what happens that when these 2 electrons, say this I am diagrammatically represented, you have 1 s or 2 s electron here, they have described by possibly the same quantum number, say same quantum, but when they mix up together, since they cannot have the same quantum number, the energy level splits up. It splits up like this, like this. So, you form a bond, and most of these good conductors, they have valency 1 and capacity of S cell is 2 electron. So, what happens when they split up into these? You have, if n number of atoms form a bond, which is diagrammatically shown here, a certain number, each has 1 electron. So, all electrons, they must have slightly different, although they are still S cell electron, they will have slightly less energy, and which is diagrammatically shown over here. They try to fill up the lower level first and they go up. And since the capacity of this band is 2 electrons per atom, and if it is a monovalent, only half of this is filled up. And this highest level of that occupied energy, this is called Fermi energy. And in fact, a characteristic of metallic bond is these electrons which are free to move, they are shared by all atoms. But here this pictorially shows the interaction of the outer electron only, how this outer electron that in energy level split up when you bring more number of atoms close together. But in reality, most of the elements you have electrons moving in several orbits, and which is shown here. When you bring these, each of these orbits, they will split up into bands, and some of these bands they will be overlapping. So, characteristic of metallic bond is you may have several outer or valency bands, and they will be overlapping, and this band will have plenty of vacant spaces for the electron to occupy, and this is why the electrons move freely. Their energy can go up, and they have good conductivity, both thermal as well as electrical conductivity. It will be a good exercise to look at the atomic structures a little detail. Say this is what I just explained a little before, that closed outer cell, this is most stable, and closed outer cell in most cases it will be 8 electron in the outer cell except for K. And we explained how to arrange the electrons in different subcells. This is in case of argon. Say suppose this is, it has an atomic number 18, and its electronic structure can be written like this, and this is the outer orbit. You add these, this is 8. So, this has a stable outer cell. So, likewise with argon, all the inert gases, they have stable or octet structure in the outer cell, and they have very low melting and boiling point. It will be good idea for you to look at the handbook and find this for inert gases. Now, beyond this, if the atomic number increases like potassium, the atomic structure, that electronic structure will be that of argon plus the 4s cell will contain 1 electron. So, this is all alkali metals, they are good conductor, they have monovalent 1 electron in the outer cell. Look at the periodic table elements from potassium to zinc and try to find out a correlation between the atomic, that electronic structures of the atom and the melting point. Somewhere in between you have elements which has very high melting point. Try and explain why it is so. Now, having explained that metallic bond little detail, see basically this metallic bond which I explained, and diagrammatically it is represented here. Characteristic of the metallic bond is it is a good conductor, and primarily the charge carrier as these free electrons, and the strength of metallic bond is proportional to the number of free electron. So, if this number of free electron increases, the bond strength goes up. Apart from this metallic bond, we have commonly known bonds as ionic, which forms between, let us say, take an example, the bond that forms between sodium and chlorine. Sodium has 1 electron in the outer cell 3s, whereas chlorine has 7 electron in the outer orbit 2 plus 5. So, the chlorine will try to get and attract an electron from another element, and sodium is one such element which can give this electron from the outer shell easily. When this electron goes out, the sodium becomes positively charged, and when chlorine gets this extra electron, it becomes negatively charged and they join together. And the force of attraction is primarily one of electrostatic in nature. And here these electrons are not free to move, therefore, these have insulating property, they are bad conductors as such. Another important bond is a covalent bond, and I talked about it in context of the structure of carbon, structure that forms in diamond, where carbon atom is located at the center of a tetrahedron, and you have 4 other carbon atom occupying the corners, and each of these 4 bonds, they are covalent. Something similar to that forms in an hydrogen molecule, molecular bond. Hydrogen has one outer shell electron, where the capacity of this cell is 2. So, it is half filled. So, that way, and if 2 hydrogen atom they share the electrons together, the structure will be even more stable and something like this, but these electrons are not free to move, and therefore, in this case type of bonding also gives insulating properties. Materials having this type of bond will be insulator. Apart from this, you have a relatively weak bond called van der Waals bonds. Now, here, so many of these cases, the charges they are not distributed symmetrically, like one over here. Even if you look at the chlorine atom, you have a nucleus, you have electrons moving around. Now, center of that electronic charge and center of that and the nucleus may not coincide, leading to the formation of a dipole. Something similar happens here when H2O molecule forms. This is oxygen mixes with 2 hydrogen atom, form a water molecule. This develops as a dipole. These centers of the positive and negative charges, they are not located at the same place, and because of that they act as a dipole, and one molecule of water, it gets attracted to, like this hydrogen gets attracted towards the oxygen of another molecule, and this type of bond is called, because of dipole, is called van der Waals bond. And because of this, water is liquid. Because of this van der Waals bond, the water is liquid and it has a dielectric property. In fact, it brings down, say, this type of ionic crystal, they are soluble in water, because water brings down the electrostatic force and sodium chloride dissolves in water. Now, let us look at the atomic bonding in all these cases a little closely. If these atoms are far apart, there is no force attracting, and interaction is very little. We say that energy state is 0 somewhere here. If you bring them closer, the force of attraction leads to bond formation. This is the force of attraction. But if you try to bring them very close, then that electrons in this orbit and this atom, they try to repel each other. So, there is a repulsive force as well. So, this gives you the state of energy, and so normal equilibrium position is one where the energy of the entire set is minimum, which is over here, and this is the equilibrium distance. And if you represent this energy as u, this u here represents that energy. It has two parts. So, this part is attraction, this is the repulsion. And you can try to find out when is this minimum. To do that, you can differentiate this du dr, equate it to 0 and find out at what r this is equal to 0. And pictorially, if we come back, if we differentiate this at this equilibrium position, the net force acting on it is 0. Equilibrium means there is no force acting on these atoms, it is 0, and which is shown here. And if you try to displace it slightly, so slightly this side, then the force become positive. Positive force means it will come back to this way. If you try to, so that means if you try to disturb it from this position of equilibrium, there because of this bond there will be a natural tendency for it to come back. Pictorially this is shown like this, it goes up but comes back. Similarly, if you try to push it, if you try to decrease the distance, then also it will try to come back to its position. So, which you show, you try to, it comes back. So, that means in that case this repulsion force becomes dominant. And here again the primary bond, these are the 3 primary bond, and this is the secondary bond is the van der Waals bond. And in all these cases, the interaction energy can be given by an expression like this. And here, if you try to represent this using a Taylor series around that position of equilibrium where the distance is r naught. So, this is what has been done. This is a small displacement. If you express this in Taylor series, this is the expression that you get. Now, here this part at r equal to r naught, this is 0. So, therefore, this change in energy is therefore represented as a square by 2 d 2 u, and all this are at r equal to r naught. Now, if you differentiate this with this displacement, then what you get, this is equal to d 2 u dr square. So, basically this is called a constant k, which actually is, if you try to push it, this first differential, this gives you the force. So, this is k, and maybe if you assume this energy is represented by this, you can try and find out k as well. Now, let us try to look at that atomic bond structure, let us try and find out what is the specific heat of a solid. Specific heat, to calculate, there is a two components. One, when you heat a metal, the energy of each atom goes on increasing. Each atom you can, it is not stationary, it keeps vibrating about a mean position. You can approximate that as a harmonic oscillator. When you increase the temperature, energy, this oscillation increases. This has two components, kinetic energy and potential energy. Each of these, average of this is equal to half k T. T is the temperature in degree absolute. This is K is the Boltzmann constant. So, the total energy of this oscillator is K T. Now, the total energy will be how many atoms you have. So, this, if you say the molar specific heat, multiply this by the Avogadro number. So, in that case, this Avogadro number times Boltzmann constant, this is equal to R and T. And if you differentiate this with T, so that when T goes, so you have R. Now, point is here these atoms can oscillate in 3 directions. So, it has in say 3 degree of freedom. So, therefore, this is to be multiplied by the degree of freedom, which is 3. So, in that case, this atomic specific heat, this comes as 3 times R, and which we know very well that all most metals, they have a specific heat around 6 calories. So, therefore, it says that the electronic specific heat should be very low. Is it really so? This diagrammatically shows the way, that means temperature we are talking about is the room temperature for most metals, they have high melting points. So, this is the one. So, here it matches, but if you go down to absolute 0, experimental measurement has shown that specific heat goes to 0 like this. So, let us try to calculate specific heat, the electronic contribution of the specific heat. If you assume that electron can move freely, it has it can move in 3 directions x, y, z. Each direction will have an energy associated k T by 2. So, therefore, this is the degree of freedom, and each mole will have Avogadro number of electrons. So, in that case is this, it is quite significant, but in reality it is not so. Why is it? Now, if we look at that band structure, so basically the occupancy of these bands, they are determined not by Boltzmann statistics, by statistics called Fermi-Dirac statistics, which gives probability of occupying a cell having an energy level E I, which is represented like this. So, here the maximum probability, this is 1, this is 0, and it is plotted as a function of energy, and this is the energy called E 0, we call it Fermi energy. And what it says that at absolute 0, the occupancy rate is maximum here. And what is, let us try and find out what is the number of electrons which will contribute towards this. We can assume an area, say kT, kT. So, that means this side is kT, this is kT. So, twice kT times this. So, not all the electrons. So, that means what we do in this case, we have quantum mechanics is applicable, and because of the quantum mechanics that all electrons do not contribute towards that specific heat. It is only the electrons which are near the Fermi level, they only can absorb energy, and if you try and contribute, this may come out to be maybe 1%, 2 kT, it may be 0.01%. So, that means this is the main advantage of this type of descriptions of the metallic bonds, that metals are made up of, they have free electrons which are shared by all atoms, but these electrons are arranged in orbits several energy levels up to the Fermi energy level, and beyond that you have vacant states where, and this determines, this gives the conducting property, and this also explains the specific heat, and similarly it can be extended to explain the electrical conductivity as well. And maybe the next class we will try to look at some of these thing again and try to explain this in terms of crystal structure, particularly the metals have very simple crystal structures, although the crystal structures of all, there are large number of crystals varieties are possible, but in metals they have very limited and simple crystal structure. We look at the atomic arrangements in simple metallic crystals and how they are arranged and how they affect the property, and then move on to represent some of the crystal directions and crystal planes, the atomic arrangement, different crystal planes, and with and maybe some of this exercise, if you go through, will help you to understand and follow the lecture and follow the subsequent lectures. Thank you.